actually be delighted to, but you know.
I was almost done. I'm Jorge Nocedal, period. And I'm very thankful to have the opportunity to be here at the Simons Institute. All right, so one of my students here has done a lot of the ideas I want to present here. So I just want to give credit to these people here. I'm going to talk about two problems here. First of all, we want to minimize a smooth objective function when derivatives are not available. Problem number one is derivative-free optimization. I have observed people developing methods for this problem throughout the years. I don't think I've ever given a talk about this subject, derivative-free optimization. I've been observing people develop methods, and there are some things that are missing. I want to develop methods that are scalable into like 1,000 variables. I want to be sure that the algorithm is parallel. Why can't we do parallel function evaluations in these algorithms? And I want to use the information that I have from function values to create something better than linear models. But I don't want to create something what Katya called fully quadratic model. If you ever attempt to do a fully quadratic model, it's not going to be scalable. That's what my claim that I will make. Now, you evaluate functions, right? You're going to have to know how to evaluate, how to place the evaluations of the functions efficiently. I think it's going to be key and how to do this. After we look at the deterministic problem of derivative-free optimization, then we're going to say what happens if there's noise in the function. I would like to use the same approach. And the key of this is to use some noise estimation techniques that are classical in numerical analysis, go all the way back to Hamming in the 1960s. So if I have a noisy function and I want to minimize it, the first thing I want to do is estimate the level of noise. With that level of noise, I'm going to be able to get a finite difference interval to do finite difference gradient approximations. So in this talk, we're actually going to fall back and say, how do I know how to create quadratic models that I know how to solve in a scalable way? And after trying everything else, I see that the only way I know how to do that is going back to quasi-Newton methods. So we're going to go and do quasi-Newton methods with finite differences. In the noisy case, something that people have considered to be a very risky thing to do. And in order to do that, we're going to have to be adaptive. We cannot make definitive decisions of what the noise is or what the finite difference intervals are. The algorithms are going to have to find out when they make a mistake, go back and correct what they are doing. But we're already able to solve problems with thousands of variables, derivative-free optimization problem, no problem whatsoever with or without noise. Now, I'll present only one convergence result in this talk. This talk is going to be mainly algorithmic. I'm going to present one convergence result to a neighborhood of the solution. So what do I want an optimization for noisy functions to do? I want it to go to a neighborhood of the solution that's determined by the noise level. And I want to show that I can converge to that quickly, linearly. Now, before I start, everybody keeps making reference to the very first talk in this symposium by Alexander, where he talked about how far should I trust my model, right? So I'm going to go and talk about something else. I'm going to talk about non-smooth optimization and why we were quite surprised there about the power of quasi-Newton updating. All right, so suppose that I want to minimize the absolute value function. And I want to use a quasi-Newton algorithm to do that. Now, I'm going to be very precise with Ben about what is the definition of a quasi-Newton algorithm, because it's going to be very important in this concept. OK, so it's a model, right? Any iteration that looks like this is coming from a quadratic model of the objective function. So we're going to do non-smooth optimization by creating quadratic models of the objective function. Doesn't that sound like the wrong idea? Right? So in Alexander's talk says, I cannot trust my model beyond this point. It's not valid anymore, right? So what would be a Newton model of this function in this area? It's a straight line, right? So I should not move beyond that line. And in fact, the observation of Lewis and Overton is that the reason quasi-Newton methods work is because they're always forced to look beyond the kink, right? The problem in non-smooth optimization is that you make a guess of how the objective function looks like, and suddenly, boom, you get a surprise, right? Suddenly there is non-smoothness, and it throws you off. What is a way to solve this problem of getting thrown off by a kink? Well, one way to do it is always make sure if there is a kink to go through that kink so that you observe the objective function before and after the kink. If you do that, then you can create a smoothing model about that, and things will work. Okay, so if you apply a quasi-Newton classical BFGS with no changes whatsoever in the way they're implemented to minimize a non-smooth function like this, it will work. It will get very close to the solution. And the reason for this is if you start here, whatever model it is of the objective function, it's going to tell you to move this way. But now the line search is the key, right? In quasi-Newton methods, it tells you, whenever you move from here to here, it's not enough to have reduced the objective function. The gradient, the directional derivative of the objective function has to increase. So don't stop the line search until the derivative has increased, right? The derivative here is constant. So if the algorithm tells you to move this way, even though you have decreased the objective function a lot, it tells you do not stop until this derivative has changed. Means the function is forcing you to go over here. So if you start at this point here, the quasi-Newton step will go over there. Now, what's the definition of a quasi-Newton method? It's a Hermite interpolant. The model here is going to interpolate the two gradients plus a function value. And it's going to do something else. Something else is the difference between BFGS and other methods. But it will interpolate these two models, and it will create a quadratic model like that. It will take a step. Then it will move this way. And the line search will force it to cross. Every time it will force to cross, every time it will create a quadratic model that is steeper and steeper. This is a very simple problem in one dimension. It's going to get you to the solution. The matrix is going to blow up and everything is going to work. But let me explain that a little bit more in detail, right? So if you apply the BFGS method with the right line search, which is what is in the textbooks, then Lewis and Overton, and more recently Frank Curtis, have found out that that's more effective than all the algorithms that had been developed for general non-smooth optimization, like bundle methods. More effective and by a wide margin. What we call the Wolf line search ensures that you always create a convex model of the objective function. This is one of the secrets of quasi-Newton updating. The line search tells you that you have to do that. Now, non-smooth problems usually have derivatives almost everywhere, so you apply the algorithm as if there are no kinks, and there may be some little things that you have to do in case you hit one of them. Now, the line search requires you have a decrease, Armijo condition, and what I called the curvature condition, this Wolf condition, says the directional derivative should increase. And this is the textbook picture of how things look like, right? So the key in making a quasi-Newton algorithm work for non-smooth problems is that when you do the line search, you should not stop anywhere here. Just because you have reduced the objective function, you should not stop here. You should wait until the directional derivative has increased somewhat, right? Where has it increased somewhat? Well, depending on what the parameter is, maybe it's here. So if I have this gradient and that gradient, that admits a nice convex model, and that's going to allow me to take a step. Every quasi-Newton update says do that, otherwise it is not well defined, and things are going to work there. All right, so this is an empirical observation by Lewis and Overton, apply quasi-Newton algorithms to non-smooth problems. And another empirical observation is that if you look at the BFGS matrix, when you converge, it has actually captured the UV structure of the objective function. So some functions that are non-smooth in some direction and smooth in another direction. And you will see that the Hessian approximation actually has captured that. It's blown up in one of the directions, and in the other one it maintains the right curvature. This is observed empirically. Now, as you convert to the solution, if there is a discontinuity, non-smoothness at the solution, then the Hessian approximation will blow up, right? And that's a good thing, because you're reproducing these kinks in the objective functions. But there's almost no theory in explaining that. I have never heard of anybody seeing a failure when applying the BFGS method to solve a non-smooth optimization problem. And people have now been trying for many years. Nobody has observed a failure. So therefore, one should be able to prove a result. They're very limited results in one dimension for very special functions. Some of us have tried really hard, and Steve was telling me there are a lot of really clever theoreticians in this building one needs a very clever theoretician to work through that theory and try to determine if this is really true, right? For what classes of functions will this algorithm work? It's too much of a coincidence that it's always working. Fine, okay. The power of the Armijo-Wolff condition is not appreciated in the convex optimization community because it is not that important in the convex optimization community in general, right? But just to go back to Steve's negative curvature case, if you have a non-convex problem, if you start doing a line search and the function looks concave, you should keep going, right? The Wolff line search says do not stop until the derivative has increased. When will that happen? All you have to assume is that the function is bounded below. And the term bounded below has been mentioned here several times. What you need actually for the convergence of BFGS is that the function is smooth and bounded below, right? So you observe that for non-convex functions. If you have a non-convex function, doing a Wolff line search produces a regularizer, a quadratic approximation of the model, but not a Nesterov type overestimator. It's a Hermite interpolant, right? And that can be a lot more powerful, right? So overestimators are great for establishing convergence results because you know that everything is for sure. These are actually sort of Taylor approximations to the function, but with the understanding that you have gone far enough to make the interpolation. You had a question, Ben?
Well, I was just going to say, so essentially was unclear to me about the Lewis and Overton paper is whether or not it's BFGS or the line search that gives you the good behavior. For example, the absolute value, if you just do steepest descent and you do the Wolff line search, you get linear convergence. And there are other cases where that also is true for the...
If you use steepest descent, it works. No, we're talking about whether quasi-Newton works, right?
I understand, but I'm just saying that, yeah. So the question is, so the Lewis and Overton paper is saying for non-smooth, quasi-Newton works well, yeah, if you do this bracketing line search.
Yeah, but of course, yeah.
Just putting this out there, and also a question to you, if you just do, pick the minimum norm subgradient and run with, just do this line search, you also get rapid convergence on these non-smooth problems.
Yeah, and my statement is, any of those methods that you produce with subgradients, we're going to kill you with a quasi-Newton method. So show me one of them, and you're going to see how these subgradient methods are blind, right? So you have a subgradient, but you don't know how far to move.
No, but if you do the line search, you do, because it forces you over the kink.
Oh, yeah, okay. All right, so good. The line search. Okay, so that was the point. What happens if you do a line search with a... Oh, no, but that's going to be a problem. No.
I believe you, but I'm just saying that the line search has a lot of juice. There's a lot of power.
The line search has a lot of juice, but you need to reproduce the UV structure, because if you have not learned, you're going to make the same mistake. You're going to come and repeat and make the same mistake, right? So once you have near a kink, you're going to have to stay near a kink. And a purely gradient method is not going to learn that. So you do need to learn the UV structure. So thanks for that question. That's where the power is going to be, right? All right, that was not supposed to be the subject of my talk. Just some propaganda here about we've been surprised about the power of quasi-Newton updating in contexts where it was not defined to work. Okay, so it continues to surprise us. A leading method for non-structured, non-smooth optimization. It's actually a great approach for doing derivative-free optimization when there is no noise. It actually competes very well in almost anything. And in this talk, we claim that finite difference quasi-Newton approximation, when done in an adaptive way, actually is also should be a leading approach for doing derivative-free optimization of noisy functions. Let me first review and make a few commentaries on the methodology that Katja went and described, right? What is one way of doing derivative-free optimization? You sample the functions, you create a model by interpolation, you minimize the model. That's the new step. You remove a point, add a new point, repeat the process. So by interpolation, you can construct that model, and in order to get a quadratic approximation to the function, you need of the order of n squared function evaluations, right? That's a lot. Now, Powell came up with some idea where you only need to interpolate n points and you use a minimum Frobenius norm update, but the arithmetic cost of these algorithms is still very high. I don't think it can be below n to the fourth. And what happens is that you're creating a dense model everywhere of the objective function using interpolation points. Where you put the interpolation points is important because, of course, you can't do high-dimensional interpolation if all the points are in a line. You get an ill-conditioned interpolant. Now, this is a theoretical problem. I don't know how important it is in practice, but that it can happen is a concern, right? Now, there's a trust region in solving this problem. That's good. That's natural. That helps you actually control things. But can these methods be made to parallelize? And I don't know if they can be made to parallelize. I know that people have done that. But what I'm going to describe here parallelizes in a completely natural way. Yes?
Since you have so many samples, can't you use some leverage, score sampling and reduce the computational cost by an order or whatever these guys get, and get an inexact solution to that quadratic model? Just do some clever sampling of whatever you want to sample there, and reduce the computational complexity. Would that make these things faster?
So you want to create the same model but solve it inexactly?
Yeah.
Right. I don't know how to do that.
I mean, in some sense, you solve a system of linear equations, you can definitely solve it inexactly, but then, yeah. But I actually want to comment, this n to the fourth is only if you were trying to do really accurate second-order models, right? Otherwise, whatever number of points, so it doesn't have to be n to the fourth. So number of samples, as long as it's bigger than n, allows you to fit some curvature.
But let's not call it accurate quadratic model. Let's call it interpolant-based quadratic model.
Well, yeah, but I'm
purely.
just, okay, but I'm talking about that you're using the, you're talking about quasi-Newton after all, right?
Yeah.
So if you're trying to, quasi-Newton after a certain number of steps is not going to have proper Hessian approximation. It's going to have something approximate. So it's similar in that sense.
And I think you were not here when you said, I do not want to do that. I don't think you're going to end up with a scalable method if you try to get a model that tries to interpolate the function everywhere, right? So let me hold on your question. How about if I go to the next slide when we contrast the two approaches? We've not written a paper, and we have a long discussion of the pros and cons about these two approaches. So can it parallelize? Can you decrease the cost, and so on? Well, let's see. Those are open questions. But what happens if you do finite differences? And there's no noise here. I'm just talking about just doing standard stuff, right? So you approximate the derivative by finite differences. You spend n function evaluations just to do any move, right? So that's a significant cost. But then how do you construct a quadratic model? You just say, BFGS, give me that model, right? At every iteration, I'm giving you gradients, give me the model. And the good thing about this is that, the difference is we're interpolating gradients and not functions. This is a very important distinction, the two different approaches. We can do the linear algebra cost and ON work because we know how to do limited memory quasi-Newton updating, and that's a very low cost. So the last thing that is going to worry me now is the arithmetic cost. The placement of where the function evaluations is done, because it's finite differences, is going to be forced to do an orthogonal set. So they're going to be spread out by definition. The points were used, but not for interpolation, the points for producing a gradient. Now, the gradient contains a lot of information. Now, there is no possibility of you for creating ill conditioning, like when you have interpolation, because BFGS is an overwriting process. So therefore, if you do something and then you do something that is contradictory, the last piece of information overwrites the last one. So provided you do the right Wolf line search, this is going to be a stable process. And this method parallelizes quite easily during the evaluation of the gradients, right? So I'm not saying one is better than the other one. I'm trying to put some things together, and then maybe we can wrap up at the end to see what is fair and what is not fair. Now, why am I talking about this now when this is nothing but taking an old code and doing finite difference approximations? Why are we talking about this now? I think there was a perception for a long time that doing n function evaluations just to do one step is wasteful. And rarely in the literature of derivative-free optimization do people say, well, let me compare with finite difference quasi-Newton updating. It's almost never done, right? So otherwise we would have detected throughout the years how the two things work. But why is this not new? Because tons of people are already doing derivative-free optimization via quasi-Newton updating. For instance, if you go to MATLAB, you say, well, here's an objective function. You don't give the gradient. You say it's smooth. MATLAB will do finite differences quasi-Newton, and that's the way it will solve the problem. And that's the same thing that our software Nitro will do, and so on. So nothing of this, of what I said here, is new. This has been done before. There's always the risk in choosing the finite difference interval because the second derivative estimate is always there. Things can go a little bit bad. The only question is whether it's competitive, right? And that's where we spend a little time doing some tests. And I'm going to skip this because I'm running behind. You know, our numerical experiments say if you do model-based trust region methods, or if you do the finite difference quasi-Newton updating, in terms of function evaluations, they're comparable. In terms of arithmetic cost, it is way cheaper to do the quasi-Newton approach, and we're solving today problems in thousands of variables, no problem whatsoever, right? So you have those two things. Fine. That part is boring, quasi-Newton updating. Can you really do it with noisy functions? So that's the subject of this. Don't look at that graph. That's the subject of this talk here. So suppose now you have an objective function that has additive noise or maybe multiplicative noise. And let's suppose today that what we have is the objective function is the sum of a smooth function plus some additive noise. And the additive noise is going to be bounded, and it's the only assumption we're going to make. And the question is, how do you do a finite difference BFGS method? Well, our approach is the following. First, you're going to invest some function evaluations in estimating the noise. It's going to be, the noise is going to be a standard deviation of this function here. You're going to spend some effort estimating the noise. That will give you a finite difference interval. It shouldn't be too small, otherwise noise shouldn't be too large, nonlinearity. Then you take a step. You work with the algorithm unless something goes bad. The noise estimation we're going to use is not one of these super expensive sample average approximations. It's going to be some randomized approach. If it fails, and the line search is going to tell you if it fails, then there's going to be a corrective approach. And it's going to say, what did you get wrong? Did you get your noise estimate wrong, or were you unlucky with the line search? And it will do something about that. So we'll need to modify the line search. And then, of course, if you have a noisy function, it is clear that the choice of the finite difference interval is crucial, right? So if it's too small, you're differentiating noise, and the algorithm will really break down. It's going to be a terrible algorithm, right? And if the finite difference interval is too large, then, of course, the gradient is not accurate enough, so you're going to have to do that correctly. All right, so the definition of the noise that we're going to estimate is the standard deviation of this quantity here. We're going to denote by epsilon f. What we detect is the noise. And then how is this estimated? So this is a procedure of Moret and Wild. I don't know how well known it is here. We have found it to be extremely effective. It does the following. I'm at a point x. I want to know what the noise level of the function is. Choose a random direction. Evaluate the function at, say, 8 points at spacing of, say, 10 to the minus 2. And then produce a finite difference table as follows. That's math. As follows. So I have a function. I evaluated at 7 different points. 0 is the base point, and 10 to the minus 2, I evaluate the function at those points there. Then you take the difference in the function values. And then you take the differences of the differences. And you continue that way. Now, you don't take the differences and divide them by h. You just take the differences, right? So these quantities here, if f is a smooth function, and I start taking more and more differences to that, these quantities should go to 0. In fact, the second one should go to 0 like h squared, and so on. If they don't go to 0, it's because there's noise. And taking differences from noise will actually be constant. Now, if you take enough differences, you'll be able to detect the level of noise. Now, in the previous slide I jumped, there was a formula for how do you use this table to detect the noise level. And this sigma k is your estimate, the standard deviation. Here we're after every finite difference, we're getting an estimate of what the noise level is. For this problem, this is the original problem, the noise was 10 to the minus 3 times that, right? So if you look at this table of finite differences, you see that the noise level is being estimated fairly quickly through the finite differences approach. But there is an observation that Moret and Wild make that is really good. And that is that whenever there's a change in sign, you should realize that you're there. You've already detected the noise, right? So how could it be that I'm making differences here and suddenly there's a change in sign? This is because the noise is beginning to dominate, right? This is already a level at which you probably are pretty comfortable at taking the finite differences. Now, just to be clear, how expensive is to do this noise estimation? Well, we did 6 extra function evaluations, and all these differences are for free, right? You just compute differences of functions, so you can do all of them. You extract from that the noise estimate, and from that you're going to get a formula for the derivative. So this is the formula that tells you how to get an estimate of the noise based on the finite difference table, and there are convergence results about this. All right, so once you have an estimate of the noise, the finite difference interval for forward differences is given like this, and for central difference is given like that. And this is very familiar to everybody who's done numerical analysis. This is what you get when this is round of error. The square root of machine epsilon is what you do. Here you get the square root of the noise. And there's always a term, the second derivative term, this third derivative term. And often people say, well, that's 1. Or maybe we'll have to estimate it, right? So if you have to estimate it, there's going to be extra work. You have to be want to be really careful, you will do that. All right, so I'm going to present this algorithm. Looks too boring, but it's not so bad. Here it is. Give me a starting point. I take a random direction, evaluate the function 6 times, and estimate the noise. Boom. Compute the finite difference interval, forward differences. Compute an estimate of the gradient. That takes you n function evaluations. Then compute a quasi-Newton step. Classical, no change whatsoever. And then you do a line search. This is BFGS. So we're going to do an Armijo-Wolff line search. We're going to try to get those 2 conditions. And there are 2 possibilities. It worked. Let's forget about this block. If the noisy line search worked, why should I reject it? I'll take the point. I look at the curvature pairs. If the line search worked, this quantity here is positive. I can add that to the memory of limited memory and continue. So the only difficult case is what happens if in the line search I had trouble. And what do I mean by trouble in the line search? We're going to do the line search, but we're going to limit ourselves to how many attempts we're going to do. And we're going to relax it in some way. If the line search works, does not work, then we're going to have a recovery procedure, right? So you have an algorithm that is estimating finite differences, and suddenly it fails. There are 2 possibilities. You estimated the noise wrong. In this case, why don't you re-estimate the noise? The other one, it looks like the estimate of the noise is fine. The finite difference interval is fine. Maybe just the line search set you off, confused you. So in that case, just produce some other move by some means. That's more or less the description of the recovery procedure, which I think I just mentioned here, and I think there's no point in getting into those details, right? Maybe I shouldn't get into that. Maybe I should stop here and just try to shoot down my algorithm. Yes, Katya?
No, but just, yeah, I wanted a quick comparison with the filter and the scale in the next slide. So.
It's not comparison with implicit filtering.
Yeah, in terms of like how he adjusted, I don't remember.
What happens is that I was going to use my hands instead of these slides. Let me try to describe again what the recovery procedure is. We're going to use a stencil. This is where Kelly's ideas come from is from a stencil, right? Okay, so if the algorithm succeeded, fine. If during the line search I have trouble, I'm going to do two things. First of all, I realize at the starting point, I did a finite difference approximation to the gradient. I evaluated the function n times, right? How about if I store the lowest function value that I saw during the finite difference approximation? And I'm going to call that f sub s. And that's what appears here. I'm going to keep that as a reference point, right? So then, what is the procedure going to do? First of all, something wrong happened, therefore, re-estimate the noise. But don't re-estimate it along the random direction, estimate the noise along the search direction where you're moving. So do those 6 extra function evaluations to get a new noise level and a new finite difference interval. Then compare the new finite difference interval with the one you were using. If they were similar, then you're going to do something. Things look good. If they don't look similar, then you have to re-estimate the noise, right? But so if they don't look similar, then you take the new estimate of the finite difference interval and you get out of there, right? Otherwise, you take a tiny perturbation. Just say everything looked good. I'm going to perturb the function. And then I'm going to see here certain tests, right? So I perturb the function a little bit, and I see, is it better than all the points that I saw in the stencil? In that case, I should take it. Otherwise, if the points in the stencil gives you sufficient decrease, I'll take a point in the stencil. Because actually, that's going to drive a convergence theory. Pattern search method theory is going to drive you that. So there's going to be a backup mechanism that will work in the deterministic case. In the noisy case, it's not clear at all, right? But that's roughly the idea of what you do. You re-estimate the noise and so on, and the details are not completely there. All right, so the line search. So you attempt to satisfy the Armijo-Wolff line search, and we know that this is always possible in the deterministic case if the function is smooth and bounded below. But if there's noise, this can be problematic. In particular, if you estimated your gradient poorly, it may not even be a descent direction for your underlying smooth function, right? So you may be trying to do a pointless line search, right? So the line search strategy is going to be to limit the number of attempts you do to try to satisfy the Armijo-Wolff conditions. If you cannot do it in 5 points, then you do the following. You're going to relax the Armijo condition by the level of noise that you have there. And you're going to try to attempt to solve Armijo-Wolff. Wolff is very important that you have because you need the curvature condition. So this is the way the line search is being attempted to be satisfied, and you have 3 possible outcomes. You satisfy the possibly relaxed Armijo condition, Armijo-Wolff condition. Only Armijo condition is satisfied, or none of them is satisfied, right? And in fact, in order to get the algorithm to be effective, we accept a point that satisfies the Armijo condition, but if it doesn't satisfy the Wolff condition, then the pairs cannot go into the quasi-Newton updating. That's the only restriction that there is, right? So those 3 cases they're differentiated. And here's a couple of numerical results. We have done tons and tons of numerical results. And these ones I will explain. What do we have here? The number of function evaluations. And this is the gap between the objective function and the optimal value. These are simple problems for which you know the exact value of the objective function. And what we're trying here is a code that Katya gave us. I think it was written with Luis Vicente. I mean, it's a prototype code. It's not the sophisticated this or the other one. This is a model-based trust region algorithm, right? And I don't think it has any special features for noise, right? We just use it like that and started injecting noise. And the method was remarkably robust with respect to noise. It was working well. And it started, deteriorating only when the noise was very high, right? And then you have a finite difference and a central difference approximation to the gradients. And what do we see? Well, we see variability of results, right? But, and for instance, in this particular case, the algorithms are, sort of competitive in terms of function evaluations. Then the trust region method finds itself in a situation where it's adjusting the trust region. One problem about the way the code is written is that if the trust region becomes too small, it has no option to make it bigger. Because once you're troubled, you make it smaller, right? And so when there's noise in the objective function, it has to be changed, right? So that's unfair to make that comparison. The code is then struggling and getting stuck in there. And in this case, the central difference, well, the forward differences was having trouble there, but the central difference gives you pretty good approximation to the problem. And here's another example where pretty much all the codes work well. But there's still something to be recommended, I think. Because suppose that we were able to show that the model-based trust region algorithm and the quasi-Newton, finite difference quasi-Newton method took about similar number of function evaluations. You know, the arithmetic cost of the two approaches is so different, right? So I can scale one so much. There would be one, and also in some sense relatively easy to implement. Okay, so I will just finish by proving one result. Because something I guess you were wondering, as you said, well, you described an algorithm that is adaptive there. Can you prove a convergence result for that algorithm to a neighborhood? Well, I don't have that yet here, right? We think that we can be done, and the stencil is very important for that. Instead, we're going to give a proof for a constant step length algorithm in the presence of noise, just to see how the machinery works. So suppose you have a function with additive noise. Twice differentiable is the underlying function. Everything is nice. You have strong convexity. Suppose that the eigenvalues of the quasi-Newton matrix are bounded. Otherwise, you get into this huge analysis. And assume that the noise is bounded absolutely, right? By the way, the Hamming techniques for estimating noise are assuming that noise is IID. So there are possibilities. There are several possibilities for the noise estimate not to work correctly. All right, so what can one prove? For a fixed step length, there's a beta between 0 and 1 such that if the step length satisfies those conditions, L is the usual Lipschitz constant, then we get that the algorithm converges linearly to a neighborhood of the solution. So this is a linear convergence result. There's a constant term here. This is a result of the form of Nedich and Bertsekas. You converge to a neighborhood of the solution where this quantity here depends on the noise. So here's the noise estimate enters there. You converge linearly to that point there. I wanted to make sure to stop early so people could shoot me down. And so I will just make a couple of provocative comments here to try to instigate more attacks, right?
There's no dimension dependence here. Where's the n?
A number of iterations.
This is the finite differencing algorithm, yes?
This is the finite differencing algorithm. This is the number of iterations. K is the number of iterations, right? So this is pretty normal, right? The starting point, the difference, the gap with the starting point.
Rho depends on the dimensions somehow implicitly? What's alpha and beta?
Well, every iteration is n function evolutions, right? So there's a dependent there.
Does full finite difference?
Yeah.
Okay.
Okay, great.
Is there a way of incorporating some sort of constraints?
What constraints?
Like even simple constraints, because for example, even if you had interval constraints, your line search may, like it may not find the way to have like well-defined the next iterator.
The Armijo condition is going to be a problem. And by the way, this is a comment that now goes to non-smooth optimization, right? In non-smooth optimization, what happens if I'm getting interfered with that, right? So already Andreas Wächter and one of his students wrote a paper on how to do quasi-Newton for non-smooth problems when there's bounds. And then so they're doing some projection mechanisms so that they were doing the Armijo line search in the right subspace. So you do that in 2 stages, and you identify things in such manners, right? Okay, all right, so what were my provocative remarks? you're going to do optimization based just on function values. You're not going to do random search. The dimension is going to kill you, right? So one of my concerns was dimension. 1,000 variables, no way you're going to do that. People have developed pattern search methods, and coordinate descent is one of those, right? Moret and Wild wrote a beautiful paper showing that the Katia-type methods, the Powell-Katia-type model-based methods, are so much more effective than pattern search methods if you apply them to general derivative-free optimization. So the real contender here are these models that Katia have developed, where you start, you evaluate functions, you create a linear model. As you get more information, you start producing a quadratic model, and you go that way. And there's a nice theory about them, right? Now, I've observed all of this work, fantastic work, and there are two things that always worried me. One of them is the cost and the concept of doing a model by interpolation. And the other one is whether really it could be done in a parallel way, right? So given those two things, and I thought, I want to do the model creation in a different way. I don't want to do it through interpolation. Every time I see interpolation, I see my hands tied. So then my colleague Andreas Wächter was doing some convolutional. I saw other people doing that. And then when I thought about this, and when I talk about this, I thought about this for 2 years. I realized the only way I know how to produce models that I can solve in ON time is with quasi-Newton updating. And they do good stuff. So the motivation there was put all the effort then in estimating the derivatives. Don't put so much effort on the model, put the effort on estimating the derivatives. And be ready to fail there and to recover if you have a difficulty there, right? So then now we have interpolation models of gradients versus interpolation of function values. BFGS is doing its magic that we sort of understand, but not quite. And you can do the function evaluations in parallel, right? So let's have those mechanisms, and the other ingredient was just use noise estimation in order to compute finite differences, and that's it. So I thank myself again for finishing on time.
You're on time. We have time for questions. Thanks, Steve.